This lecture will provide an example of improving computational complexity by carefully designing an efficient algorithm for calculating polynomials and their derivatives. First of all, let's consider a naive algorithm to evaluate a polynomial. The standard form for an order n polynomial p of x consists of a set of coefficients a0 to an and corresponding monomial terms x0 through xn. One way to approximate the execution time of an algorithm is to count the number of operations between floating point numbers, including additions and multiplications. For a second-order polynomial, 2 additions are required between monomial terms. 3 multiplications are required, including 2 to evaluate the quadratic term x squared. A third-order polynomial requires 3 additions and 6 multiplications for a total of 9 floating point operations. A fourth-order polynomial requires 14 floating point operations. The number of additions and multiplications scales in a predictable manner. Evaluation requires 1 addition for each monomial term. The term describing the number of multiplications required is actually a well-known expression known as the triangular number, which has a simple analytical expression. Simplifying the resulting polynomial and applying asymptotic big O notation indicates that the computational complexity of this algorithm is order n squared, or quadratic. Another option for calculating the polynomial is to represent it in nested form. For example, the second-order polynomial a0 plus a1x plus a2x squared can be rewritten by factoring out the x from the second and third terms. In this case, the polynomial would be evaluated from the innermost coefficient a2. Consecutive multiplications of the variable x are therefore applied to all previous coefficients, eliminating the need to evaluate the monomials independently. Note how this evaluation would work for a third-order polynomial. The innermost term will be multiplied by x 3 times, resulting in x cubed, without doing the excess multiplications in an independent loop. Looking at the second-order nested expression, we see that a total of 2 additions and 2 multiplications are required, for a total of 4 floating point operations. The third-order polynomial requires 6 floating point operations, 3 additions, and 3 multiplications to evaluate in nested form. The fourth-order polynomial requires 8 operations. Extending this pattern to any potential order n polynomial, we would require n additions and n multiplications, or 2n total floating point operations. By applying big O notation, the constant term 2 goes away, and we see that the resulting computational complexity is linear. As demonstrated earlier, this is a significant improvement in computational complexity over evaluating the polynomial one monomial at a time. This is also the current standard for calculating polynomials. One interesting thing about evaluating a nested polynomial is that the algorithm is identical to synthetic division, or the division of one polynomial by another. Let's look at the division of a polynomial p of x by the first-order polynomial x minus 2. We set the polynomials up for synthetic division by constructing a tableau consisting of the coefficients of p of x, or the dividend, on the right. Using the standard synthetic division algorithm, we negate the divisor and place all but the highest order coefficients on the left. In this case, only a positive 2 is kept. We then drop the leading coefficient, a 1, down. We then multiply this value by the divisor and move the result under the next coefficient. Summing this result and the corresponding coefficient gives an answer of 2. Multiplying this by the divisor produces 4, and summing produces a result of 10. Multiplying and summing produces the fourth result of 13. And finally, multiplying and summing again produces the final value of 34. We can assign each of the resulting values as coefficients to a polynomial that is 1 order lower than the original. The final coefficient, 34, is the remainder term. This polynomial is the result of the division of p of x by x minus 2. This remainder term is also the result of plugging 2 into p of x and keeping the remainder term as the result. Now let's compare the synthetic division algorithm to the evaluation of a nested polynomial. We'll do this step by step. Assume we want to solve p of x for x equals 2. We first set up the nested version of the polynomial. In both cases, we consider the highest order coefficient of the polynomial, 1. To evaluate the innermost sequence in the nested polynomial, we multiply by x, which is 2, and add the next coefficient, 0. This is identical to the next synthetic division step where we multiply by the divisor, 2, and add the result to the next coefficient. The next step in both algorithms takes the current term, 2, and multiplies it by 2 to add the next coefficient, 6, and get 10. We then multiply this term by 2 and add -7 to get 13. And finally, we multiply by 2 and add 8 to get 34. The steps for both algorithms are identical, meaning that the remainder term for synthetic division is equal to the value of the polynomial p of x for x equals 2. In other words, we can evaluate a polynomial at x for any value c by applying synthetic division with a divisor of x minus c. This algorithm, used to evaluate both a polynomial as well as perform synthetic division, is known as Horner's algorithm. There are a few benefits to this formulation, so let's make sure that you understand exactly what's happening here by going over the process one more time in more detail. Now, assume that we have a fourth order polynomial p of x. Dividing p of x by x minus c gives us a new polynomial q of x that is 1 degree lower than p of x and has a remainder term. From our previous comparison, we expect this remainder term to be the value of p of x evaluated at c. So let's prove that that's the case. We first set up our tableau for synthetic division by writing out the appropriate coefficients. We drop the leading coefficient, and then multiply by c and add the next coefficient. Notice that I'm keeping all of the terms without simplifying. When we multiply by the next coefficient and add, notice that we start building up a nested polynomial that increases in order at each step. In fact, the final result produces the nested form of the polynomial p of x, with c substituted in for x. The take-home message here is that synthetic division of any polynomial p of x by x minus c will produce the nested form of the polynomial p of x evaluated at c for the remainder term. It's important to understand this relationship because it provides some additional benefits beyond just the ability to evaluate the polynomial. When we perform Horner's algorithm, each step produces the coefficient for a new polynomial, which we'll call q of x. Let's reset our tableau and reevaluate with the divisor c, this time keeping track of the intermediate values. We'll annotate these coefficients b0, b1, etc. The remainder term, which is the result of the polynomial c, will be annotated r. The resulting polynomial q of x is 1 order lower than p of x and contains our remainder term r, which is actually p of c. We're going to use this new polynomial, which is composed of the intermediate values produced by Horner's algorithm, to prove an additional benefit. Let's first use this intermediate polynomial to provide an analytical proof of the relationship between synthetic division and evaluation of the polynomial. Let's make this proof as general as possible by starting with a polynomial p of x with arbitrary order n. Using synthetic division to factor out x minus c yields the polynomial q of x consisting of n new coefficients b0 through bn minus 1, as well as the remainder term, which we've noted is just the result of the polynomial at x equals c. Let's collect the intermediate coefficients into a traditional order n minus 1 polynomial r. Since we got this result by dividing out x minus c, multiplying both sides by x minus c gives us the original polynomial. The term on the right-hand side consists of a reformulation of the original polynomial expressed in terms of c and the new polynomial r. This formulation shows why synthetic division by x minus c provides us with the result of the polynomial at c. If we plug in c to this expression, the only remaining value is p of c. The rest of the expression, including all intermediate terms calculated when building r, go to 0. This theoretical basis gives us the tools we need to look at an additional benefit of Horner's algorithm, which is the ability to quickly calculate the derivative of a polynomial. Once again, starting with an arbitrary order n polynomial p of x and a value c, I've shown that you can calculate a new polynomial q, which is just p of x divided by x minus c. Since the remainder term is equal to the polynomial evaluated at c, this gives us an alternative expression of p of x equals x minus c times the main part of the polynomial plus p of c. If we calculate the derivative of p of x using the chain rule, we get x minus c times the derivative of the polynomial r plus the polynomial r. We lose the remainder term p of c because it's a constant with respect to x. Now, note that if we evaluate p prime of x at c, the derivative term r prime of c goes to 0, leaving rc. This means that the derivative of p of x at c can be evaluated by finding the solution to the polynomial r of x at c. Note that this polynomial is produced as a result of Horner's algorithm. Therefore, 2 passes of Horner's algorithm will allow us to compute both the polynomial and its derivative at c. Both of these are computed in order n time. Let's look at some pseudocode for Horner's algorithm so that you can understand how simple it is. For input, we assume that we have an array of coefficients, starting with the highest order monomial. We also supply the number of coefficients, which will be required for most programming languages. We also require the value of x, for which we'll be evaluating the polynomial. The output is an array of coefficients q, which has the same number of terms as c. However, the last term at q n minus 1 is the remainder term, or result of the polynomial p of x. The first thing we do is check to see if there are 0 coefficients. If there aren't any coefficients, the polynomial is undefined. Here, we'll just return 0. We then initialize the first coefficient. The highest order coefficient is identical for both p and q, although remember that q is a lower order polynomial. Next, we enter a for loop, starting with the second coefficient with an index of 1. Each iteration of this for loop evaluates the innermost term of a nested polynomial and updates q. Finally, let's consider an implementation of Horner's method in C++. We won't go over the details of the implementation internally, but I encourage you to think about the most efficient way to design it. However, we can look at how an efficient implementation can be used. Now, let's assume that we've implemented Horner's algorithm with the following function signature. Here, C is an array of length n holding the coefficients of p of x in descending order. N is the number of coefficients, which is required to evaluate the function, and x is the dependent variable, where we're evaluating p of x. And finally, q stores the output, which is an array of length n containing the coefficients of r and the final result, p of x. Now, assuming all of the relevant memory has been allocated, we can call this function once, which will overwrite c with the new polynomial and store the result in Cn-1. Then we can call Horner's method again, passing the new polynomial array, but noting that it contains one less coefficient, since the value of n-1 contains the result of p of x. We can then store both results in variables for use. Now, I'd like you to think about how you would implement a function that you can leverage in this way. How would you do it efficiently, and would you make any changes to the interface that I'm proposing here? Don't feel limited by what I've described. Feel free to use more advanced C++ data structures such as vectors if you find them more convenient.